Q minus W. But for a control volume, we use the enthalpy because of the work of the pressure of the fluid that comes in and goes out. That term, as you remember, H equal to U plus PV, and therefore this is the work of the pressure. And therefore we combine these two, and now we have H for an open system. Okay. Therefore, let me see where did I end the lecture. Yes. Now, therefore, for the control volume energy rate balance, control volume, and by the way, if Sambuda is going to bring the exam with him actually today, the grading exam. Control volume energy rate balance. We saw that if this is a control volume with some inlets, exits, and let's say flow in, right? We put an imaginary control surface around this. So this is the control surface and the control volume, and inlets, exits. Therefore, rate of change of energy inside the control volume with time is equal to Q dot of the control volume minus, someday I'm going to remove this, minus the W dot of the control volume, right? Plus summation over all inlets, M dot I, and therefore HI, VI squared over 2 if there is any significant velocities. Because usually these terms are much smaller than this one, than H. And then plus GZI minus sum over all exits, M dot exit, H exit, V exit squared over 2 plus G Z exit. Okay. Therefore, we'll be dealing with this equation. And for the steady state situation, therefore, imagine continuously flow comes in, flow goes out. Therefore, no change inside the control volume. Therefore, dE control volume by dt is 0 if I have a steady state. Okay? And this is the energy rate balance. Remember, in positive, yes? Out, W dot is positive, because out already negative is taken into account. In, again, positive, out, the negative. Okay? And this is the balance between all of these. All right. We also saw that for a single inlet, single exit, etc., this is the main equation that we will be using therefore. Now, some components of a cycle that we look at now. First thing, nozzles and diffusers. A nozzle versus a diffuser. In a nozzle, flow is accelerated velocity increases because area decreases. So this is an example of a nozzle here. Flow in, flow out, area 1 larger than area 2. Okay? So if this is a nozzle, for example, the inlet to a jet engine, okay? Then a diffuser. Okay. Area increases. Station 1, station 2. Okay. Here again is station 1, station 2. There is no shaft, right? So no shaft work in these cases. Only I can have heat transfer maybe Q dot. In real life, there may be some heat loss from the flow to the environment. And here also maybe. Okay, so that's the maximum that is involved here. For aerospace applications, sometimes we have a converging, diverging nozzle, we call it. So it's a nozzle and a diffuser. Okay? So effectively, for aerospace applications. In these situations, therefore, what do I have? If the area is increasing, I have V2 larger than V1. According to Bernoulli's equation, remember that in case, but I don't know if you have seen the Bernoulli's equation. But generally, velocity at 2 increases compared to the velocity at 1, and P2 is less than P1. In this situation, V2 is less than V1, and P2 larger than P1 for these cases. Okay. Then, here, for example, if I want to, later you will see in fluid mechanics, MAE 101B, if you want to get a supersonic flow, okay? We must go through a converging, diverging nozzle, we call it. Okay? This accelerates now the flow less than basically subsonic, then supersonic we achieve here. Now the process is, again, a combination of fluid mechanics and thermodynamics aspects of it. Okay. For nozzles and diffusers, therefore, I see that W dot of the control volume is 0. There is no shaft here. And at steady state, what do we have therefore? Rate of change of mass of the control volume with time is 0. Also, dE control volume with time is 0. Right? In addition, I have Z1 equal to Z2, right? Because it's just straight. Whatever it is, it's a small component, but there is no elevation difference between these 2 points. Therefore, for mass, I have m dot 1 equal to m dot 2. We just call it m dot, mass flow rate. Okay, you remember m dot is rho velocity area. The density times velocity times area in general. Therefore, the energy equation, based on what we have seen here, is 0 equal to Q dot control volume. Let us divide this equation by m dot. now that m dot is fixed, m dot plus one exit, one inlet, h1 minus h2, right? One inlet, one exit, plus h1 minus h2, plus v1 squared minus v2 squared over 2. Everybody agrees? So this becomes my energy equation in a nozzle or a diffuser situation. Okay. Any questions about this? So it's a very simple, actually, system. If you want to accelerate or decelerate the flow, at some point we use a nozzle or a diffuser. Then B, the turbines. How does the turbine work? The turbine has some blades, and there is an inlet, to the turbine, and then there is exit, right? Imagine. And this turbine has a shaft here. So flow comes in, flow goes out. Imagine steam comes in, high pressure, high temperature, and the steam goes out, lower pressure, lower temperature. So all that energy is converted into shaft work. And therefore we have these, these blades here that turn, and therefore create the rotational motion of the shaft. As a result, we get work out of this. So one set of these blades, for example here, right? Around the shaft, it looks like this. Yes? The fluid hits these blades, rotates and causes rotation. And because of it needs to slow down as far as giving of its energy, right? Giving away its energy. So it must expand, as you know. Therefore, the blades at the end are larger than the blades at the inlet. Okay? Why? Because remember the TV diagram. Imagine you have superheated steam that is coming into this turbine. And so you are somewhere here. Right? And if you are giving away some of the energy, therefore it comes like this to this line, P1, P2. You agree? Along that path, the volume decreases, the volume increases, 0.1, 0.2. The pressure decreases, of course, and the temperature decreases. So this enthalpy change is converted into shaft work. Okay. So this shaft basically rotates because of this flow through here and out. Okay, so we get shaft work, for example, in a steam turbine. We get work out of it. So here I have a higher energy gas or fluid, Here I have a lower energy gas. Same equation applies, let's say under steady flow condition, 0. If there is any heat loss from the turbine body itself, this is non-zero. Work out, of course, it gives us work. Then one inlet, one exit again. Z, no change practically in a turbine. Even if the turbine is the size of this room, so what? Okay? Delta Z, negligible. Velocities, if we know the velocities, fine. But for superheated steam, these terms are so small compared to the HI and HE. Okay? So practically you have m dot in H in minus m dot exit H exit, W dot control volume, if this is non-zero, and Q dot control volume equal to 0. Same equation we use therefore for it. Okay? So, mind you, it can be a gas turbine or a steam turbine. Okay? A gas turbine, therefore, air in a jet engine. Just to show you, I think I drew the jet engine the first day of the lecture, but let me erase this part. So in a gas turbine engine, air comes in, right? And this is mounted on the body of the airplane, on the wings. The first section is a compressor, which I'm going to show again soon. So a compressor really compresses the air in order to bring it with high energy into the combustor part. So here we have the burning process happening here. So this is the compressor with a shaft, of course. This shaft, it continues and goes to the turbine. So compressor, the combustor, and the turbine. And then we have a nozzle or a diffuser, yeah, practically. So what happens here is that this shaft, the turbine work turns also the compressor, and some of it is left for other things practically, if we need it. So here I have fuel coming in, injected here, fuel. Air comes in, of course, they burn here, and the combustion products go through the through the blades of the turbine, and then they exit through the diffuser here at the end. Therefore, a turbine can be a gas turbine, like we see here, or a steam turbine fixed in a power plant, in that kind of a cycle that I have over there. Okay. So, therefore, a compressor, we put work into the compressor in order to do what? To compress. Therefore, this is a compressor here. The blades of the compressor are larger at the inlet, become smaller and smaller, right? And then the gas goes out like this. So gas comes in, gas goes out. Okay, and therefore they have a shaft work again. We put work into the compressor. W dot control volume is in here. Here I have W dot control volume out. Because the turbine gives us work, the compressor needs work. Okay. So in general, under steady state conditions, just like the other one, I have 0 equal to if there is any heat loss from the compressor, from Q dot control volume. This is the control volume around this. Minus W dot control volume plus 1, 2, right? H in minus H out. H1 minus H2. Fine, this may be negative. Okay? Because H2 is larger than H1 for sure. We are compressing it, increasing the pressure, increasing the temperature. Therefore, enthalpy is larger. And then plus, if there is velocity change important, V1 squared over 2 minus V2 squared. Okay. So what happened here? For both a turbine and a compressor, many times these are insulated, so Q dot is 0. For a compressor, we put work into it, yes? Therefore, this W dot is negative. Negative times negative is positive. And that takes care of these two negatives. Right? Because they are now negative. H2 is larger than H1. Gas has a higher pressure, higher temperature, also higher velocity at V2. Okay? Compressors, therefore, are used for gases because we are actually compressing it. For liquids, we have pumps instead of the compressor. Same principle, but we use a pump now. Therefore, for liquids, we use pumps instead of the compressors. And pumps have different actually designs and everything, but in general still there is some maybe, I don't know, blades and everything. Liquid comes in, liquid goes out at a higher pressure. Why? Because if this is for steam, if this is for water, you see that I'm going now from, let's say, here to here by a pump. Right? It doesn't have to be only water. I can use other liquids as well. For example, refrigerants and things like that we can use. Okay. Then, so this was C, the compressors and pumps. B was the turbines. A was nozzles and diffusers. So after this is D, heat exchangers. Let me erase here now. Heat exchangers. D. These are the elements of different cycles and things like that. Heat exchangers, as the name implies, we exchange heat between two streams of fluids. It can be one fluid, can be gas, another can be liquid, okay? Or can be two fluids, two liquids, or two gases, it doesn't matter. Therefore, here it's something called direct contact heat exchanger. A direct contact heat exchanger. In this case, let's take this exchanger and imagine I have fluid coming in at some pressure and temperature, P1, T1. Same fluid coming in at another pressure and temperature, condition 2, P2, T2. They mix and the result goes out at station 3. It's a direct actually contact. So what happens is it really we mix them and send them out. For example, okay, steam coming in, cold water coming in. Mixture goes out at some condition of the mixture. Okay. An example of this, sometimes we call it an open feed water heater. This is a good example. Okay. Open feed water heater. And it's a direct contact. Then we have, let's say B. We have a tube. Within a tube within a tube. Counterflow heat exchanger. Many different actually types, but these are just some of the major ones. What happens here? I have a heat exchanger here, like this. Okay. So what happens? This fluid comes in, it goes here like this and gets out. It really engulfs the inner tube, let's call it. So another fluid comes in here and goes like that. Okay, so what happens? Let's say I have a steam here coming in, very hot. I have liquid water coming in. Out goes maybe hot water. Okay, and this steam loses energy to this outer fluid around it. Okay. It does not have to be a single tube, it can be multiple. Actually going back and forth until it gets out. Okay? To increase the exchange area for heat. Yes, sir?
Is there a reason why the flow is called a counterflow heat exchanger?
Yes, because this is coming from the end and gets out there. This is coming from the right, goes to the left. Counterflow is more efficient, generally, okay, because it gets, there are parallel flow also. Both can go in the same actually direction. Yes. So different types based on the different designs. So as a matter of fact, if this is the counterflow, the parallel flow is this one. Tube within a tube, C. Tube within a tube. Parallel flow. Heat exchanger. Same thing, but now I have yes, and then this one, and then this one. From here, of course. Right? And then it goes out here. Okay, so parallel flow heat exchanger. And then we have something called the cross-flow heat exchanger. Many different types, of course. Cross-flow heat exchanger. This one. Let's say I have yes, and this arrangement, right? Let's say these are passages for fluid. For example, fluid goes out of these, okay, in this way. Then I have flow going in between these sections. Here, here, right? You see how it actually works out. Imagine sheets, and these sheets, of course, are not solid. Fluid is going through them, and then outside these sheets, I have flow going in the other direction, exchanging heat. Okay. Example, automobile radiator. Right? Air flows through those, through the section of the radiator, outside of it. And then inside you have the water going that is getting cooled. Okay? But they are not, of course, in contact, unlike the direct contact. They are separate flows. Okay. So these are this is a good example of what a condenser, right? I remove heat from my primary fluid, which is this one, through a secondary fluid, imagine. So heat goes from this into this. Q dot, we called it Q dot condenser or Q dot cold. And what is the result? This heat is coming out of this flow, right? And goes for, I don't know, district heating, imagine. okay, or heating the campus, right? But this section here to here is across the condenser. And you remember, if you have a cycle like this, imagine this is the 1, 2, let's call it 3, 4, P2, P3, right? This is the condenser part. Agree? Therefore, you see that from superheated steam, I've converted to liquid water by going from superheated steam, this is 0.3, this is 0.4. Right? And this heat that is removed from here, you do remember boiler, the turbine, yes, condenser, pump. Okay, so this is really 3 to 4. 1, 2. Heat, Q dot hot, right, for boiling. W dot the turbine. W dot pump into the pump. Q dot cold. Later in chapter 5 and 6, we are going to see we have to remove some Q dot cold for a cycle to work, based on the second law of thermodynamics. Okay? Any questions, anything? Now, for each one of these, as you know, I have what? dE, dt, control volume for the last time. dE dt control volume equal to Q dot minus W dot control volume, sum M dot in HI VI squared over 2 GZI minus sum exit M dot exit H exit V exit squared over 2 plus GZ exit. Any term that is not present, we drop it, right? Okay, steady flow, usually. dE by dt gone. For a heat exchanger, there is no work, right? Only heat transfer. So W dot control volume is gone. Okay? Q dot control volume. If this is perfectly insulated, right? There is no heat loss out of this, right? Therefore, I write this energy equation for flow number, what should we call it? Flow A, right? Write the energy equation. For flow B, write the energy equation, right? Q dot between the two must be equal. Okay? And I know the other conditions. Enthalpy at the exit, inlet and exit for A. Right? Velocities, if given, fine. If not given, fine. We don't care. Z, elevation is insignificant. Therefore, you see that just with enthalpy and mass flow rate for the A, and mass flow rate again for B, and H exit, H inlet of B, I can balance and find the Q dot from one to the other given them. Okay? Therefore, energy equation applies to every one of these. Bunch of examples in the book. Please, okay, review them all. No showstopper here. The only thing that is a little strange that we have never seen before is a process called a throttling device. And that is a fascinating thing because you can really drop the pressure and yet keep the enthalpy intact. Throttling devices. Here we get significant reduction in pressure. By introducing a restriction into the line. Through which gas and liquid flows. Gas or liquid flows. Okay. This happens by partially opening or closing a valve. Imagine I have a valve here. Or to that effect, a porous plug can do the same job. Valve, here is the this is an example of a valve you close or open it, okay? And therefore you cause more restricted flow or less restricted if you open it. Therefore, flow goes in, this is now my control volume here. Right? And therefore, flow goes in, flow goes out here. Therefore, partially opening or closing a valve. Notice that here, in a porous plug, you have a porous plug, this is just a passive system, right? It just simply drops. Now, it changes the pressure, of course. Okay? Similarly here. Now, the equations. Mass. Notice that dm control volume by dt equal to m dot in minus m dot out summation m dot in minus, so 0 equal to m dot in, imagine, minus m dot out exit. That's it. So m dot in equal m dot exit. One inlet, one exit. Then energy equation. under a steady flow condition, if I have a steady flow, therefore I have 0 if there is heat loss, Q dot control volume minus W dot control volume plus M dot in, one inlet, one exit, H in plus V in squared over 2 plus GZ in, delta Z is insignificant, minus M dot exit, H exit, V exit squared over 2, GZ exit. Okay? And so let's say these are not contributing. Okay. Let's say no heat loss, no work. M dots are equal, right? From this I see that H in plus V in squared over 2 equal to H exit, V exit squared over 2. Right? Just by dropping those. In many, many cases, kinetic energy is negligible compared to the amount of enthalpy that the gas or fluid is carrying. Therefore, generally, let me write it here. If kinetic energy negligible in many cases, then H1 equal H in equal to H exit. Okay. The best example of a throttling process, as we will see later, will be in a, let's say, again, temperature specific volume. High pressure, right? Let me call it P prime, right? P prime less than P, right? Imagine I have a process that I am here, saturated liquid, and I want to drastically drop the pressure using a valve like that, or we call it a throttling device. I go like this, boom, go to a much lower pressure by that, and here I have 1, 2, H1 equal to H2. Therefore, if you know your condition here, imagine, of course you know, because you are given that I have a saturated liquid at such pressure. You go to the saturation table, you read everything. Then you want to find what is my final state at a pressure much lower than that. Let's say if this is, say, I don't know, 20 bar, you drop it to 5 bar, right? Find this state. What do we do? The only thing we have is H1 equal H2, right? Therefore, you know your H2. You go to the saturation table at 5 bar. Agree? P prime is given to you as 5 bar. P is given as 20 bar. The state is saturated liquid, you know H1 from the table. H2 is equal H1 You go to the saturation table for pressure at 5 bar. You read Hg. You read Hf. Yes? You find X at 2. Knowing that you know H2, you know Hg, you know Hf. You have identified your final state for this throttling process, and you have dropped now the pressure to much lower ones. Okay? This is generally used in a refrigeration cycle, which we are going to see later. Okay, it can be ammonia, for example, okay, or refrigerant 22 or what. Okay. Therefore, remember this from now on, guys. For a throttling process, H1 equal to H2. Throttling process. H1 equal H2. Because otherwise you are in trouble. You want to reduce the pressure somehow, right? The best thing is to just pass it through a throttle. Very good. I think Mr. Sombuda is well enough that you have fully recovered, right? Okay, great. A few problems now tomorrow in the problem session he's gonna solve regarding these. These are from chapter 4 that I gave you, right? Yeah. Okay, guys, where are we again? Let me see. Okay. Introduction to chapter 5. This chapter deals with the second law of thermodynamics. And please just get a coffee, sit down with the examples of the book, right? And go through these examples one by one. Okay? Once you fully review them, that's it. There is nothing outside what is in those examples. For a heat exchanger, you have energy equation for one stream, energy equation for another stream. Q between the two is the same. Okay, that's it. You can solve the problem. Here, for this open feed water heater, what do we have here, therefore? Let's just take this example, right? You are given m.1, given m.2. State 1 is given. State 2 is given. Okay? What is the enthalpy at a state 3? If a state 1 is given, you know H1, right? From the table, imagine. If a state 2 is given, now let's say pressure P1 and T1 are given, and this is superheated steam. You can find H1 from the superheated tables. A state 2 is given as a, actually, I am making up now this problem. State 1. T1, let's say, 800 Celsius, I don't know, I think the tables are given in Celsius, if I'm not wrong, right? P1, 15 bar. Fine. You go to the tables, you check, and you see that this for sure must be superheated. State 2, P2, because it's open and everything, same 15 bar. x2 0.65, right? Then state 3, P3, 15 bar still, same pressure. What is T3, H3, etc., right? Or do we at all have X3 or not? So, just by looking at this, I see that on a TV plot, let's say 15 bar is here. Right? Let's say this is a state 1. Right? This is a state 2, imagine. X is 65, so state 2. Right? State 3, same, now pressure, but how do I actually find these now? I know that m dot 1 plus m dot 2 equal m dot 3. Agree? Same fluid. Also, let's say there is no heat loss from here. Q dot equal to 0. Right? This is a mixing device. I've insulated it. Yes? No work, no heat transfer, and the problem is a steady flow. Therefore, what do I have here? Remember, I'm making up this problem. I don't think we will run into any problem, but so what do we have? dE by dt, I have erased it. I always erase it and I need it. Just like this, right? Velocities are kinetic energy negligible compared to enthalpies. Therefore, what do I have over there? In m dot multiplied by h. So m dot 1 h1 plus m dot 2 h2 exits now, right? Minus m dot 3 h3 equal to 0. Agree? No Q, no W, no dE by dt, no delta Z, no delta VI. VI squared equal V squared. That's it. I have two equations. And the maximum that I can have is two unknowns. Yes?
Just to make sure, in that equation, it's the sum of them, right?
Summation?
Yeah.
Yes, yes. This was only for one inlet, one exit.
Oh, gotcha.
That's right. Here I'm just putting the sums. Exactly. So you see that mass flow rate also comes in here and plays a role. But so this is a typical example of mixing and heat exchanger. Okay. Very good. Now, chapter 5, second law of thermodynamics. 5 and 6 deal really with the second law. In the next, let's say, 20 minutes, I do the introduction, and then on Tuesday, we wrap up chapter 5, and on Thursday, we go to chapter 6. Okay. So, chapter 5. Second law of thermo. There are a few actually theories and basically statements that we are going to look at, and as a result, we see that not every cycle is possible. Okay, some specific things must be satisfied. First is the Clausius statement of the second law. Okay, Clausius statements. Of the second law. I'm just going to say it, but I'm going to also draw. Let's say we have a hot reservoir and a cold reservoir. Okay, everybody can see here, down here, and the cold reservoir. Let's say my hot reservoir is a huge hot lake, and the cold reservoir is another huge lake but cold between the two of them. Therefore, let's say we have some kind of a device here. It can be anything, a metal bar, something, okay, that can transfer heat. So, this is just a device that to transfer heat. Between the two reservoirs. Okay. Q from the hot goes to cold. Yes? In one of these. In the other one, Q from cold goes to hot. Okay? This is possible, this is not possible. Just by itself, heat can't go from a cold reservoir to a hot reservoir. Okay. Clausius says, and just if you listen, you know exactly what he's actually talking about. It's impossible for any system to operate in such a way that the sole result would be an energy transfer by heat from a cooler to a hotter environment. Okay? It's impossible that heat just goes from cold to hot in a reservoir. Hot to cold? Yes, fine. Next. By the way, a thermal reservoir is a huge one that no matter how much heat I add to it, the temperature of it doesn't change. Okay? Let's say Lake Michigan, right? Okay. So we know what the Clausius statement is. Then there is right? It's impossible for heat to go from a cold reservoir to a hot reservoir by virtue of just a transfer without any work by us or anything that we do. Okay, next. Kelvin-Planck statement. There are these two statements by Clausius and by Kelvin-Planck of the second law. Let's take a thermal reservoir again. Okay? So let me put hot, cold reservoir. And let's go with a cycle. Now you know what a cycle is, yes? Imagine it has something, somehow, a boiler, a turbine, something, okay? Everything, but we call it a cycle. By cycle, I mean the fluid starts from one state, goes through these processes, comes back to another, to the same state. Okay. You have done homework on those, right? Maybe something like this even. Agree? Okay. I show the cycle by this. Okay. This is a system that is surrounding a thermodynamic cycle. This is the cycle here. And this is a thermal reservoir. Okay. Q cycle comes in, yes, from the thermal reservoir. Q cycle. W cycle we get out, right? Work from this cycle. Yes? Kelvin Planck statement says that it's impossible for any system to operate in a thermodynamic cycle and deliver a net amount of energy by work to its surroundings while receiving energy by heat from a single thermal reservoir. This is impossible. What does that mean? It means that it's impossible to bring heat in and get work out. There must be another thing involved here. And now you see why I must get some heat out for the system to work. So remember, just heat into the cycle and work out, impossible. That's the Kelvin Planck statement. Okay? No. Remember these two, therefore, it's impossible to have a system that by virtue of its presence, heat goes from cold reservoir into hot. Impossible, impossible here. Next, we define irreversibility. What's irreversibility? Directly it relates to the second law of thermodynamics. Reversibility versus irreversibility. Now, from now on, we define the best theoretical performance as ideal performance. Best, not theoretical. If you think of efficiency of 100% is ideal, right? But we can never get to it in general. Okay, so idealized situation has the best theoretical performance. Non-idealities are due to irreversibility. Okay? If this process was ideal, right? Where did I, okay, here. If this process was ideal, it would go back to its initial state. Okay, this is due to irreversibility in the process, right? If this was reversible, it would go back up. Okay, therefore this process is irreversible. There are almost everything in nature is irreversible. Okay? Burning fuel, right? You can never go back to the initial hydrogen state. It's now hydrogen and oxygen. This is an irreversible actually process. Okay. What are different types of irreversibilities? Heat transfer from one state from one medium to another. Right? Once heat goes out of this room, it won't come back unless we do something to it. Agree? If I want to bring that heat back, because it's lost in the atmosphere, if I want to bring that heat back, I must do something to my system. Okay, another thing, unrestricted expansion of a gas, right? You have a piston cylinder here with a stop here. The gas is high pressure. Yes? You remove the stop. The piston goes to here. Now it's equilibrated with the surroundings, the pressure. This is now an irreversible process because it won't go back to its initial state unless we do something to it. A spontaneous chemical reaction, as I mentioned, a spontaneous mixing of matter at different compositions. Friction, another process. Friction is an irreversible process, right? Because you are losing energy. You are giving away energy in the system. Okay. That said, another one. Inelastic deformation, right? This is an irreversible process. It won't go back to it. It's ruined. Right. Okay, so you know what irreversibility is. An ideal process is one that is reversible. Okay, but how do we actually get to that? Irreversible and reversible process. During a process of a system, during a process, irreversibilities may be present within the system or within its surroundings. This means, guys, same thing, right? Within its surroundings, or within both system and surroundings. Okay, but then what does this lead to? Actual processes are irreversible. Anything we do is irreversible by itself. Okay? You compress a spring, right? Then you release it. It won't go back. Therefore, a process is reversible when no irreversibilities are present. Very clear, of course, but it seems nonsense, right? A process is reversible when I have no irreversibilities. Okay, but present. Within the system or its actually surroundings. No irreversibilities. A process is internally reversible when there is no irreversibility within the system. Irreversibilities may be present in the surroundings, right? But not in the system. Therefore, that system is reversible. Okay. A process that is internally reversible, we call it quasi-equilibrium. You remember the quasi-equilibrium? The process that takes forever to go from a state 1 to a state 2, therefore at any instant it can go in either direction. Okay. Analytical form of the Kelvin-Planck statement now. And after this, I think, yeah, another couple of minutes for the Kelvin-Planck statement, guys. If W cycle, right, less than or equal to 0, meaning that less than 0, I have internal irreversibilities. Now, present. Equal to 0, we have no internal irreversibilities. Okay. Just to show you what we are getting into this, we are gonna, okay, I'm gonna start with the next in our lecture, beginning with this. Now that we know what a reversible and an irreversible, okay, process is. Homework I assign it, I have it already actually, now ready. There are 3 or 4 problems from chapter, where are we? From chapter 4, okay? But due on Tuesday. Okay. Just look at the examples in the book and the problems that some Buddha is going to solve tomorrow. Okay guys, take care, I see you all.